Causal Inference in Retail, an M&S story. And this is hosted by Christopher, Hassan, and Dipankar Nath over here from M&S. So Chris joined M&S in May 2022 as a senior data scientist within the decisioning DS teams at M&S. He supports the business in developing models to personalize a customer's experience online and on traditional offline channels. Dipankar joined M&S in November 2021 as a senior data scientist at the Loyalty DS team and M&S's Spark scheme. He helped build models to enable better personalization of customer offers while also creating a fully automated decision capability for loyalty campaigns. He is currently working in the customer growth and marketing team. So guys, the floor is yours.
Thank you. Thank you. Thank you for the kind introduction. I'm Dipankar. This is Chris, of course. I think everybody know that. So before, we'll be talking about causal inference in retail, as the title suggests. And just before going into the talk, just brief overview about M&S. So we are a pretty big retailer in the UK. We have around 30 million customers. We have about 17 million loyalty program customers, which you know as Sparks. We have around nearly more than 1,400 stores globally, and our group revenue is nearly around 12 billion. So what we want to talk about here is causal inference and how we use it. I'll just give a brief introduction to how causal inference works, how we quantify it. Then I'll be talking about meta learners and how we use them in here. So and talk about the application of meta learners in Marks and Spencer. Then we'll cover a few use cases which we are doing, and then Chris will talk about how we actually evaluate those meta learners and how we use them for monitoring the performance. So what is causal inference? So causal inference actually gives you a way to answer questions which are of the nature of what if. For example, if you have a headache and if you are given an aspirin, what happens to you? Or what if you don't give you an aspirin? What happens to you then? What if you give an offer to a customer? And what if you don't give the offer to a customer? Does it increase sales? And this is something like is studied a lot. What if someone goes to a private school? And what if someone does not go to a private school? Does it affect your future earnings? These are the type of scenarios which you can attempt to explain using causal inference. So there's a few terminology which I'd like to go over. So generally we use this, the field is quite influenced by medical sciences. So you can see that we give the names such as this. For example, we say that it is, if you're given an offer, for example, then we call you the treatment group. If you're not given an offer, then you call you the control group. So the outcome of this is basically, can also be a random variable, which is basically given an offer or not given an offer, you have either purchased or not purchased. Now this output, and both the treatment and the output actually can be continuous in nature. It doesn't have to be discrete variables. So it can also be, need not be discrete effectively. So how do we quantify it? So the outcome of the treatment effect is basically that here I, which I'm talking about here, is basically one unit, for example, one person here. I give them an offer. If I give them an offer, then I have a specific output, which can be either 0 or 1. And I've not given a treatment, then also you can have an output as well. It can be, you had either bought something or not. And this is what you try to estimate, which is basically the difference between these two quantities. So now this quantity is actually very difficult to measure. I'll tell you why. In order to do that, you need to be as powerful as a watcher. You need to be able to go to two different universes and watch two different outcomes at the same time. So as you can see, quite difficult to do this. So we really cannot measure this above quantity. But we still need a way to measure it. I mean, we need to estimate it. So that's why we use statistics. In statistics, we always estimate stuff. And how do we estimate? So I'll give an example about this one. So now that I've told you that at a given point of time, you can either measure the outcome with the treatment or without the treatment. You cannot measure both at the same time. So what you can do is do this experiment over a lot of people. But you can still measure something like, what you can try to measure is something like this, which is the expectation of this quantity, which is with the treatment, minus this without the treatment. This is also not that easy to compute, but we can use various machine learning methods, including very simple stuff such as linear regression to actually compute this treatment effect. So we call this, so this quantity is called average treatment effect, and that is what we can use even simple methods like linear regression to actually compute it. So what is easy in this thing is to compute is what you can easily see that this you can break down into these two parts. That's fine, that's easy, you can see. But what is difficult to measure, what is not equivalent is, because remember you can only give treatment to a group or not. So the effect, this quantity is not equal to the difference between the people who are treated minus the expectation of people who are not treated. It's not equal. This is because of a reason. If this were true, then correlation would imply causation. There are lots of interaction terms here, which I've not shown here, and that interaction is caused because of confounders. Confounders are basically other quantities which can influence your treatment, the outcome of the treatment, or the control, basically. You can remove the treatments. You can give something like, you can do something like randomized control trials. So basically, you randomly choose your treatment and control to make sure that your treatment or control are exactly the same, except that the only difference is if you give a treatment, that's the only difference you can make out of the groups. But if you remove the treatment, then those two groups are the same, effectively, prior to them actually doing something. So for example, if a confounder, so you can, for example, in the case which I was working before, like offers. So you give an offer, but the offer and the offer can be like, what is the offer is doing? It's changing the price, right? So effectively, I'm tuning price. So what I'm trying to do is giving you a different price, and I'm seeing how the sales will be there. But your price can be affected by different quantities. It can be affected by weather. It can be affected by whether you're a repeat customer. Because if you're a repeat customer, you might be more likely to get an offer in the first place. So both these things affect your treatment in the first place. And they also affect the treatment of the sales. So this is a confounder. And you need a way to remove these confounders. So while I'm talking about this, you can also see that I can also talk about treatment effect on a single customer as well. So that is something which is also quite interesting, because that is something which you'd like to estimate, because you actually cannot measure in the first place. So when I start talking about individual units or customers in this case, then what you are basically trying to answer is that given a set of confounders and your treatment, what would be the treatment effect look like? So what you're actually measuring is what is known as a conditional average treatment effect. So this you can try to measure using different methods. So computing the conditional average treatment effect, there are numerous techniques. I'll go over just one of the techniques here, which is meta-learners. So what is the basic purpose of a meta-learner? So basically what we do is you use ML models to separately predict for a unit the target, basically the outcome, when you are treated. And for the same unit, you also compute the target if suppose it was not treated. And you can compute the conditional average treatment effect using this quantity. So basically, just subtract these two outputs. So this is effectively what the meta-learner will do. So let's go to one case of a very simple learner. And that's why it's called S-learner. It's a simple learner, so a single learner. So what we do here, in this we have one model, which basically takes into account all the confounders and the treatment as a feature. And then what you do is you predict using that model for only the treatment variable, for the treatment conditions, and also for the control conditions. You get two different outputs, which is basically what I was trying to show before. And you subtract this quantity, and you get the conditional average treatment effect. This is a very good model, very easy to implement. If you have, for example, something like price, which you want to like vary over days or something, you can also use for example, continuous variables to measure this. You can measure what is known as price elasticity, and you can do all these things using S-learner. It's a very good model, and the first model you should actually use when you're trying to do something like this. But it has its own problems. Basically, since you're using one model, and what we generally do is to get a good model, we do regularization. So when you do regularization, effectively what you're doing is making the model less sensitive to most of the parameters here. So effectively, you're also making it less sensitive to the treatment. So your treatment might not the outcome might not reflect the actual treatment in the first place. So but it's fine for the other confounders, but we need it to be sensitive to the treatment. So as learners might have an issue where your model is actually less sensitive to the treatment now. So how do we go around that? So we go for a second system, which is known as T-learner or two learners, effectively. So this can be any two machine learning model, non-parametric, most hopefully. And then you create each model for each of the conditions. You create a model for control, you create a model for treatment, and then you compute the same thing, and you have and you can again measure the conditional average treatment effect. And this gives out a way of the drawback of the S-learner. Although S-learner is still a good model, I would suggest for you to use. And yeah, so it still suggests that you can go for that. Now, let's cover one of the use cases which we use. So basically, I work with CRM in the CRM space, and what we send out is what I basically work with is which customers should I select for sending out a campaign email, for example. So these campaign emails or marketing emails, this problem works for both of them. These are basically used for making customer aware of product, what products are there, what offers there are. For example, I have Sparks here, so whenever a Sparks offer come in, then it will come to me as well. So they will send out an email. Then also make aware of seasonal offerings. So basic idea is that just a sticky advertisement, don't forget to subscribe. So while sending out these emails, we need to still consider a few things. You need to send out the right campaign message. You need to reduce unsubscribe risk, because unsubscribe results in loss to the company, so you need to reduce this. And also, in general, you want to increase open and click-through rate. So in order to achieve this, we create multiple models. So we have an email open rate model, for example, a click-through rate model, and you have the unsubscribe model. Now, this is the most one which I'll be concentrating on. The other two are basic propensity models. You're just computing like probabilities. That's fine. And what we also do, we rank these customers based on these models. So we basically take all these models, combine them together with a weight-based system. And what you do is generally for the unsubscribe, you put a negative weight. So basically, people who have a high unsubscribe rate will probably have a low rank. And what will happen is, if the unsubscribe is too high, then you'll get a negative number, then you don't include that customer at all. So depending upon what is the campaign, more like not me, but more the campaign manager's choice, they might actually decide to tune all these parameters by themselves. So it's up to them. If they want to really not even consider unsubscribe, they can make it 0, it's their risk. But we give them an option. But the idea is that if this number becomes negative, you don't give that customer an email. So basically what we are trying to do is compute this uplift in subscribe, in unsubscribe, and we use this and we compute this probability using a causal model. So basically, what we have is treatment, which we basically send emails based on ranking, and then we have a separate group which is taken out previously before we even do any customer selection or something. We keep this. We send them emails, but we do not consider any rank in there. So that is like our control, and this we do it every time. Every time we send an email campaign, we do this because that helps us gather data as well. So what we do is basically use a T-learner to compute this causal uplift for the unsubscribe probability. So how this pipeline looks like. So basically, we have a filter for the eligible base. So eligible base takes into account, for example, okay, have you unsubscribed from the emails already? Then you are not part of this base. Then there are some other business criteria as well. For example, they have to be loyal customers, depending on some conditions. Then yeah, so you take that. Then you create features and merge those features together. We get a predicted propensities and causal uplift. So basically, we have ML pipelines which does this for us. So most of our tech stack is basically Spark. We use Databricks and Azure basically to do our stuff. Most of the machine learning models happens here. Most of the orchestration of our pipelines happen through Azure Data Factory. Then we rank the customers according to the various strategies. For example, they might already give us, like, if you're an email with trade driving but no offer, it's a different strategy. Basically, each strategy corresponds to different weights on the model. then we basically provide this audience to the campaign managers, and effectively they can then apply their own rules. For example, campaign managers might say that, oh, I don't want to send it to this type of customers. Then they will do their own selection on their end. And finally, all this orchestration is done, for the emails itself is done through Salesforce. And then you send out basically campaign emails with about 5% control in them. So this is how the MBAS pipelines work. And now we'll cover another use case, which Chris will cover, which is the incremental customer lifetime value. Chris.
Amazing, thanks Dipankar. Can you guys hear me? Oh, perfect. So my use case is a bit different than Dipankar's. So with Dipankar's, he has a customer base which are treated, and he also has a natural customer base which are controls. So with those bases, you can combine them together to create your causal uplift models. But we're going to look at a different scenario now where everyone's treated and we don't actually have controls, but we need to come up with a way of finding controls so we can build a causal model. So this is the type of scenario. And this scenario is retrospective, while here's his perspective, where we decide at the start who's in control and who's treated. Okay, so I'm going to go through these different topics. So the first one is just saying what is the treatment effect and the outcome variable we want to model. Then I'm going to talk about propensity score matching, which is the approach which we're going to use where we build the propensity models and then we actually do the matching to create pseudo controls. Then talk about the model, and then the interesting part, which was, I think, quite helpful, is talking about the evaluation methods we use for these models. Okay, so how do we frame the treatment effect? So on the x-axis, you've got, as a customer engages with a category, here is menswear, over time, they're going to make additional visits. So the first visit is an acquisition visit, then they make an additional visit to have 2 visits, an additional visit to make 3, and so forth. And so we're going to measure the treatment effect as being making an additional visit in a category. So that's what we're interested in. When a customer makes an additional visit in a category, what is the uplift that that's going to generate? And so what's the outcome variable that we're going to be measuring? So here, a customer makes their first visit, and then the outcome variable here, which we're defining, is the sales in the next 365 days. That's where it's the CLV, customer lifetime value. So importantly, you can see they have a treatment here, and then we measure the outcome variable a day after for 365 days. They make a second visit, and again, we look at the outcome variable. But we're not interested in predicting sales in the next 365 days. That's a regression problem. We're interested in actually predicting what the causal impact is. But to do that, we need to essentially say a what-if question, which Dipankar talked about. What if they didn't actually make an additional visit? What would their sales have been in the next 365 days? And if we knew that, then we could essentially estimate the causal effect, which is what we really want to know. Because at M&S, we want to say, we want to drive long-term value of a customer, and as a customer engages more and more of a category, what's the category that would drive that long-term value? And we frame it as an additional treatment, or additional visit, sorry, as a treatment effect. So first, what's our hypothesis of, I guess, what we expect additional visits to generate in terms of incremental long-term customer lifetime value? So here on the x-axis is the treatment, so going from 0 to 1 visit, making 2 visits, so an additional visit, getting them to 2 visits, 3 visits, an additional visit, getting them to 3 visits, so forth. The green curve is what we would expect as their sales in the next 365 days, the outcome. And the gray is the what if. Suppose we could know the what if, and we also knew that, then we could see the uplift, which is the difference, and that's the orange. So we expect diminishing returns. As a customer engages more and more of a category, we hypothesize that the benefit in terms of their CLV spend in the next 365 days is going to slowly reduce. So the next question is, imagine we could set up an experiment for this. What would it look like? So there'd be a cohort of customers, let's say they've got 5 visits in menswear and they really want to make their 6th visit. It goes through an experimental layer, and some people get assigned to a treatment, which is make their 6 visits, and another says keep with 5 visits. At the end of the experiment, we can then say, okay, let's estimate the causal effect. We've got those in treated, get the mean sales in the next 365 days, and those in control, and then we've got the uplift. But the challenge is this experimental design doesn't exist. People self-select to have an additional visit. So this approach can't be done. And this is where I was saying the distinction between the first approach Dipankar talked about and this is that we don't actually have natural controls. So we need to come up with an approach. So in this section, I'm going to talk about essentially building propensity models and then using them to do the actual propensity score matching. So first, the easy case. Let's look at the treated customers, because it just is intuitive to imagine them. So we've got our customer database full of transactions. So every time someone comes to M&S store, they make a visit. When they make a visit, that line represents a date they come to a store and make a visit. They could shop in multiple categories. So here they've shopped in 3 categories. Another day they come, and they shop in another category. Another day they come and they shop in another category. Another day they shop in 2 categories. So we've got this view of our customers. By customer and date, we've got every single category that they shop in. That's another customer and so forth. So from this, we want to create essentially these, this information. So we've got the X matrix, a W matrix, and a Y vector. So what are those? So if we take these 2 dots, they represent different dates that are important. So the black dot represents the visit date. So on that date, we can calculate the W matrix. The W matrix, basically, if we have, say, 50 categories, it's going to be 50 categories or 50 columns wide, and they're binary variables, 0 and 1, if they shopped in that category. And the number of rows is the number of visit dates. So that's what the W is. And the date just before the visit date is where we're going to calculate our X features. So I'm calling that the X features scoring end date. So as of that date, we can calculate as many features as we'd like. And then the outcome Y is defined the day after the visit date, and it's 365 days. So we can do that for one customer, do it for lots of customers, and now suddenly we've got our treated base with our X, W, and Y. So now the next bit is we want to discuss control customers. So first, we start off with this pool of candidate control customers, and they're going to be used for 2 purposes. So one is to create the propensity models, and then the second is to actually create pseudo controls using them. So first, let's just discuss how we get X features and W and Y to them. So it's quite simple. So we just take a customer and we assign 2 random dates. So the black dot represents the date we've randomly assigned, which says on that date, let's check which categories they've shopped in. The white represents where we're going to calculate X features up to. So we do that for all of our customers. And the first pool of customers is just M&S's customer base. So we've got a lot of customers, and we can assign these dates to them. Now it's straightforward. So for this customer, again, using those dots to represent the different dates, we can calculate the W vector. So it's going to say on that date, on the treatment date or the visit date, let's get all the different category binary columns and just say 0, 1, 0, 1s if they shopped in those categories. We can get X features just the date before, and again, the Y outcome variable is the date after the treatment and 365 days worth of sales. So we do that for all our customers. And again, we have now this new customer base, which is our candidate control base, which has X features, W, and Y. And now comes the stage where we build our propensity models. So it's just a giant loop. So we can loop for every single category. The first step is to filter the controls for where a customer base which didn't shop in that category, and here those who are treated, so they had that additional visit. And this bit I'm leaving like a black box, because I think everyone here is familiar with that. You have your classification model. You can do what you need to do your downsampling of your 0 and 1s. You train a propensity model. And this was done in Spark for speed and efficiency of scoring the entire base. So we've now got a model for every category. The next stage is to now do propensity score matching. So we again are going to reuse those candidate controls. So it's a giant for loop. We've got our treated customers and our control customers. We get the eligible base, so those who for any category haven't shopped on a particular day, and for those who have, we concatenate them. Then we've got our model that we can now get the propensities for. And now we put every customer into a percentile. So I said propensity score matching, but really it's percentile score matching is what we've done. And the reason we did that is because it's far more fast. We can use Spark, we can use SQL to do all the joins. And it's just easier than matching on an exact probability. So now every customer is assigned a percentile. And now here comes, I guess, the matching part, creating the pseudo controls. So what are the matching criteria? Well, one's percentile, so it's the propensity to shop in the category. So we want to say if you're a treated customer who's, let's just say, made their 10th visit in menswear, we want to match you with a control customer who's also really likely to have made that 10th visit but hasn't. So by doing this, we're able to say the control also would have made a 10th visit, but hasn't done so. And the other thing which we do is we match based on date. So this is like trying to mimic a normal experimental design where you say some people are in treatment, some people are in control. So as of the same time point when the customer who was treated made that additional visit, they've been matched to a person that's a pseudo-control, which at that same period of time was also likely to make that additional visit. And for the treatment effect being an additional visit, we also have to make sure we match on the same number of visits in the category just prior. So if someone's made their 11th visit, they're going to get matched to a control who's up to that point had 10 visits in the category. Great. So now we've got our treated base matched to these pseudo-controls. So the next question is, how do we evaluate the success of this matching? So a lot of this stuff, I guess, is more high level, but it gives you the idea. So first, we want to just check what's the match rate. So normally in like retrospective stuff, you have this question of support. So the idea of support is saying, for any treated case, do you actually have example cases where you could actually find a match? So is it so rare for a treated that it's like finding a needle in a haystack for a control? So here, I'm just showing one of the matching criteria where on the x-axis is the percentile, on the y is the number of treated cases. So here, it's like 15,000 in the top percentile, while in the controls there's plenty to match. So it's saying we have support to do the matching. And then there's more analysis you would do on each criteria to basically say you're confident that you have support for your treated base. And then the next thing is evaluating the success. So there's two approaches which we've used. One is basically using AUC. So we can take the customer base and we can say, okay, great. Before matching, we've got controls and we've got treated. Take the model we built and say, what's its ability to distinguish between the two? And then you get an AUC. And then on the match base, you do it again, and you see that the AUC is basically at 0.5. So what this is trying to say is, again with the experimental design, if you had assigned customers randomly to control or treatment, there shouldn't be any difference between the X features between the two. So if you were to say, oh, for everyone in treated and anyone in control, in a normal experimental design, you wouldn't be able to detect a difference between who's in treated based on the X features. And we're able to replicate that using this AUC idea. So yeah, we've removed the difference between treated and control when you look at the X features. The only difference is one's treated. So that's a pass. Another one, this is the table one approach that you'd see in the literature where they basically say, it's basically a Z score. So you have a difference of two populations, you get the Z score, and essentially if it's greater than 0.1, you say there's a significant difference in the population. So here we're just saying for before matching, there was 48 variables where there's a significant difference. After, there's 2. So again, you've basically another way of saying that what's a success. So finally, I think there's 2 sections, but I'm going to go quickly over this because I don't think this is as interesting as the evaluation. So we want, and we're short of time, so we want to basically now train our SLA. Already, Dipankar explained this. So we've got 2 different pipelines. We combine our data, and then we have a data pipeline, which just does some general feature selection, and then we've got estimator pipeline, which just does hyperparameter tuning. And this is an S-learner for our first version. And now at predict time, it's easy. Like Dipankar said, we can basically take every customer and we can predict under treatment and under control. We can sort our customers from high and locate. And then what do we want to do? We want to bin them. Now, the reason we want to bin them is, unlike normal, in a situation of causal, we actually don't know for every customer what's the alternative. So if they're treated, we don't know what they would have had if they were in control. But luckily, when you put customers into bins, we can actually say in, for example, the top decile, there are some customers who are treated and some customers who are in control. And at the bin level, we can actually say, let's take everyone in treated, take the average, let's take everyone in control, take the average. And the difference between the two is the observed K at the bin level, and that's the best we can do with causal. So now we're going to talk about evaluation. And I think this bit's the most interesting. Okay, so we're going to talk about first lift. And look here, it's easier. So I'm defining pseudo formulas, but the first formula is N group decile. So for N treated, for a particular decile, I can say how many customers are in that decile. Y group decile says for, say, Y treated for a particular decile, give me the sum of the outcomes to the 365 days. And I can say for the predicted K treatment for a particular decile, I've got the predicted K for customers, just sum all of that. And now comes, I guess, the simple equation. And this is the bit which I think is opaque sometimes when you read literature, but I'm just making it clear. It's literally saying for a bin, take all the customers who are treated for the outcome, get the average, take everyone in control for the outcome, get the average, minus the 2, that's the lift. And then and that's also the Kate for that bin. And below, I'm giving you what the predicted is. So the predicted says, you know what, in the bin, you do know for every single treated or control what the model would have said. So let's just sum those predictions and just get the average. And then you get this. So all of this is real data, but I've hidden everything, so we don't actually see it. But with the lift, let's go back. I'm going to quickly, so with the lift, you have a monitor. So here are the bins. So it's usually in deciles. And then you've got the blue, which is the observed. And then you've got the gray, which is predicted. So there's two things with lift. You want to say, is it good at discriminating? So a good model will basically have this monotonically decreasing relationship for the blue. So we can see it's done a good job at putting high treatment effect customers with low. And then another thing is reliability, which is the gray, which says, is your model reliable? So a model doesn't have to be both, but in this example, it's doing good at also being reliable. So just like in probability, where you calibrate your probability model, in this situation, we're saying this is also calibrated well. And then the next lift metric is cumulative lift. So with this, if as normally in marketing we say, I don't want to go up after maybe the decile 1. We want to say, I want to go up to the top 2 deciles or the top 3. So it's the same idea with this. We've got the lift curve, but now we're going to create a cumulative version. We say, I want to go after the top 3 percentile or the top 12 percentile. And normally this is framed in percentiles rather than deciles. So it's the same exact formula as lift, except now we're doing cum sum. And then with this, the key thing I would just highlight is when you go after everyone in the base, right at the end, that's going to be equal to the average treatment effect. So take everyone in treated, get the average, take everyone in control, get the average, and that's what this is. And just as a way to know that you're not going crazy or that your model's working, you can always generate a random like predictor. So just np.random.normal and just literally use that as a benchmark to see if everything's okay. The last one I'm going to talk about is cumulative gains. So with this, I need to define, I guess, a few more things. So one is this idea of the cum sum n. So with cum sum n, you're basically taking in any percentile the sum of customers in treated and control. That's the first definition. And depth is basically just the percentage version of it. So if you went up to the top percentile, that's 1% of the base. The top 2, that's 2%. And then you've got 2 definitions of cumulative gains. And it depends on if your model's reliable, which one you can use. So if your model's reliable, it's probably form 2 is okay to use. Because you're making a super strong assumption that says if you go after the top 2 percentile of the base, you take the absolute number of customers and you multiply that by the cumulative lift. So you're saying you rely on that and you're going to say to the business, this is the real pound value you're generating. The other one's based on like percentage. So you take the cumulative lift curve and you multiply it by a percentage. And it looks like this. And this is nice because it looks something like we're familiar, and you can like calculate area under the curve and other metrics on this. Now, the final thing is like an added thing I thought would be nice to show you guys is what happens if you've got customers where you can have a negative treatment effect. And I'm going to go through this quickly, and there's something benefit I can show at the end. So here, for example, you can see the blue. The model does good at discriminating, but it's not reliable. It just can't predict how negative things are going to be, but it sees who's going to have a negative treatment effect. So this is saying giving them the treatment effect makes things worse. It was better if you kept them as controls. So that's what it looks like from a lift point of view. From a cumulative, you can see this massive change in the slope. Now, from a cumulative gains, you can see this side. So this is essentially a good way of like detecting a cutoff point where you say you wouldn't want to speak to more customers. This is a situation where from the business, there's actually a limit of how many customers you speak to. And now, because I know there's probably no time for questions, but there was one last thing I was going to say, is we created a repo where you can go to, and then from that you can play around with all of the causal evaluation metrics, so it's easier to actually in your own time play with code and actually understand it. Because I think the causal evaluation metrics is probably the useful thing to get your hands dirty with. So that's everything.
One more slide.
Oh, one more slide. Go. What's the last slide?
Yeah, just an advertise around. We are hiring, so please feel free to scan this, and this will take you to our careers website. Thank you.
Thank you so much. We will now be taking questions. We have 5 minutes, so if you have a question, please put your hand up.
I wanted to ask about the newly registered customers and the customers who have shopped in the number of times less than 3 times. So we have talked about the customers that shopped for 10 times, so we can make a decision using causality on it. But the customers that have less shopping habits decrease the accuracy of the models, I guess. How can we increase the accuracy of our models for this type of customers? Can we use the demographics of other customers who have shopped and, for example, can be in the same gender and as age or shopping in the same category? Thank you.
I think that's a good question around like, so when I showed the diagram of like treatment effect, I just framed it in a simple additional visit. So I think what you're saying is as customers make fewer visits, the model may be less accurate. Is that correct? Yeah. So I think what I've not done is profile the different, I know it's the hypothesized sort of view, yeah. I think there's stuff where I can do more analysis on just seeing for each of the different treatments, specifically to like going from 0 to 1 or 1 to 2, how well the model does. But there is this thing where my focus is on discrimination rather than reliability for my use case. But there is something to also bear in mind is there are lots of other categories customers are shopping in. So even if someone's new to to a category, like say they start shopping in kids wear, we've got a history of their purchase behavior in other categories. But you're probably right, there's more uncertainty in the early stages when they make a few visits.
Yeah, I just had a question about the meta learners. So my understanding of this is definitely very basic, but the whole point of causal inference to me is to basically understand the correlation versus causation, right? Answer what is correlated and what's caused. If you're using the meta learners, which are essentially just modeling correlation, are you then not baking in correlation into your causation argument, in a sense?
Do you want to answer it?
Yeah. We are not. So basically, this is something which also Chris covered in his. So basically, when we build the meta learners, we also do propensity score matching. So what you're trying to build out is basically the goal of the only way you can compute causal inferences if you have both the treatment and control are exactly the same. So I mean, we cannot make that, but you can make sure as close it is to. The goal of matching is to actually do that. So before Chris actually computes his treatment effect, he actually does the matching first. That makes sure that if you take out the treatment, those two groups are basically the same. So what we have done is removed any sort of correlation there, and the only thing which is there is basically the causation, and that's how we try to work our meta learner suite. So similar problem is faced by the same model which has the same bias. So basically you have to make sure that your treatment and control which you are creating the models for, they are equivalent. So and the only difference is when you just put a treatment in there. So that's what we try to do. So without that, it will be, you'll have like just correlation in there. Yeah.
Okay, I have a question on propensity score matching. Why did you guys choose this method over all other like potential matching method? And whether do you think clustering would work in this sense?
So I kind of decided to do, it was what would scale, because we've got lots of categories, and then what could I use Spark easily with? And if you coarsen the matching criteria, it scales really well with SQL. So making the probabilities into percentiles coarsens things, and you can do matching, and then afterwards it's evaluating the success. So that's why I use the AUC as well as the significant mean difference. But the real reason is it's scalability. So when we're doing stuff, there's over like almost 45 categories, and it's going to be increasing. So the training time will be something around 4 or 5 hours for building all of those. Scoring is around 30, 40 minutes. So so that's the main motivation. And then there's other probably improvements we can make.
And also I think in addition to that, basically when you're trying to not use propensity, you're basically considering all the confounders. So you're taking all those features to do a clustering. That's very compute heavy. So this is an easier way to get around that problem and get a score for the confounder.
Yeah. So in the past, I've done like a k-means approach. So the seeds are the targets, and then you throw the controls, and then you do the matching, and that can take a long time, and then you have to do it again and again. So in the background, there's also sampling with replacement or sampling without replacement, which you can easily implement in SQL. But it takes more time doing it using like a k-means approach.
Thanks a lot.
Sure.
Well, thank you. Unfortunately, that's all the time that we have for questions.
All right.
Thank you so much. That was amazing. Can we give them a round of applause?
Thank you.
And now we will have our coffee break. And if you want to have a chat with them, you can go ahead and see them at the front. Thank you so much.